I'm very glad to come here today to share with you some of our research. Yeah, I will go through the four topics. First of all, I will give a brief introduction about my understanding of digital twin, of a digital twin. Then I will show you a prototype digital twin of IES, the cloud CSS. Then I will give two examples of the digital twin application. One is the optimal control design of the heat pump-based heating supply system, and the other is the planning and the design platform for IES. First, let's see what is the digital twin and why do we need a digital twin. If you go to Wikipedia or Baidu, Baidu is very commonly used search engine in China. You will find the definition of the digital twin. It is said that the digital twin is an integrated mod-scale probabilistic simulation of a system or a process that uses the best available physical models, sensor updates, fleet history, and etc. to mirror the life of the corresponding flying twin. The concept was publicly introduced by Dr. Michael Reed. Then, in year 2002, uh, then Dr. Reed is a professor of the University of Michigan, uh, who presents this idea at a Society of Manufacturing Engineers conference in Troy, Michigan. Actually, 2 years earlier, that's in year 2000, Professor Li Qiang, a full professor of my department, presented the concept of digital power systems. It is Professor Lu gave a definition to digital power systems as a visualized digital and real-time visual of power systems, including but not limited to the following information. If we compare the definition of digital power systems with that of digital twins, we can see they share many similarities. And you can see digital power systems actually is digital twin of power systems. Many famous international companies such as Gartner, Deloitte, Oracle have published their reports about the digital twin. For example, Gartner thinks that the digital twin is the top 10 strategic technology trends for this year and the last year, even the last 5 years. And Deloitte thinks that Industry 4.0 will not be realized if there is no digital twin. Oracle thinks that digital twins will play an important role for IoT applications. To build the digital twin, we think that we need to build knowledge-based differential algebra construction model for IES. And we, according to some physical laws, and we also need to build data-driven relevance model using mass measurement data. Those two kinds of models are fused in cyberspace to construct the digital twin of IES. Then with the digital twin of IES, we can monitor diagnostics, and optimize the operation of IES. We think long of the two kinds of models is dispensable. On the one hand, the data-driven relevance model can supplement unmodeled dynamics and stochastic information to knowledge-based models. On the other hand, knowledge-based DAE model can make up data insufficiency due to limited samples and biased samples. We think that both the state grid and China Southern grid, the two biggest uh, China electricity companies, realize the importance of information in great layered data. That's why they present the concept of the future power Internet of Things and the concept of transparent grid. Since 1998, our team has been working on uh, the digital power system, and we start from from a desktop computer to a combination of high performance computing, cloud computing, and big data analysis. We try to realize state-of losses, decision-making, and credit verification with the help of data streams. Next, I will show you a prototype display of the IES, Cloud PSS. This is the conceptual structure of Cloud PSS. It uses computing resources on cloud to accelerate simulation of IES. It connects users, devices, computing facilities, and decision agents through the internet. This is the hardware of the hardware structure of Cloud PSS. Users can access the Cloud PSS through any web browser, and GPU-based computing nodes are behind a web server and a data server. The users can submit their simulation service request through internet to the Cloud PSS. This is the software layers of the Cloud PSS. Users access the Cloud PSS from the front end on the web, and models and algorithms are in the middleware. Computing power, such as CPU-based computing nodes, are in the back end on cloud. Here, virtual machine knowledge is adopted to allocate computing tasks to computing resources. So far, there are many functions can be accessed through the internet for free. And here I illustrate some functions that the Cloud PSS has. For example, the Cloud PSS can simulate HVDC light, microgrid, and wind farm cyber physics system. And users can share their cases and models through Cloud PSS Community-based Plaza. The Cloud PSS was put online in year 2016. So far, there are more than 45,000 users registered for Cloud PSS service. They are from 19 domestic universities, 21 institutes, and 6 abroad universities. The Cloud PSS has many device and system models. For example, uh, here I give some examples of the EMC model for device and system level study. This is the detailed switch models for electrical components. This is the factor EMC model of modules. And this is the average model. This is the average model for modules. And this is the plus minus 800 and 1100 kV UHVDC EMC models with detailed protection and control. This is the models for Seedway 5-pole MMC HVDC benchmark with 76 sub-modules. This is the model for DOD, which is a key component of the solid state transformer. This is the EMC model of Sydney DC network benchmark. Here, different color parts represent different AC/DC power networks with different voltages. I want to mention that this model has more than 80,000 switches, and sub-CSS can simulate the dynamics of this system without any difficulty. This is the EMC model of a microgrid with PV and energy storage. And this is the EMC model of a large-scale distribution network model, which integrates speed, circuit quality, control, and relay protection. Multilateral parallel simulation can be conducted with this model. This is the model of a large-scale wind farm with detailed power collection network quality, independent wind generator control, full low voltage right-through protection. With this model, equivalent model of large-scale wind farms can be studied. This is the EMC model of a large-scale AC/DC power system model with more than 1,500 generators, with exciters and governors, with more than 11,000 buses, more than 8,000 transformers, 4,400 transmission lines, and 7 LCC HVDC lines. Next, I'll give you the first application of the digital twin. We'll use the digital twin to do optimal control of a heat pump-based heating supply system. Okay, this is the schematic of the heat pump-based heating supply system. Here is the power source, which drives dozens of heat pumps to supply heat to external loads. Here, the red line represents the pipe flowing hot water, and the green line represents the pipe flowing cold water. The control target is to minimize the electricity consumed by the heat pump. And how to do that? We need to switch on or off heat pump. And we need to obey two constraints. One is the room temperature should have the minimum deviation from setting and should stay within a small range. The other constraint is that the heat pump switch on and off time should not exceed a preset number. To solve the above optimization problem, we need to go through the following 4 steps. First, we set up models for thermal load, heating supply network, and heat pump respectively. Then we combine the above 3 models together to get the model of the floor heating supply system. Then we do simulations with the obtained heating supply system model and predict the variation of room temperature, check the environment temperature change, and heat pump usage. Then we find the optimal control of heat pump. We set up the thermal load model, the heating supply network model, the heat pump model, and combine them together to construct the digital twin of the heating supply system. Actually, the digital twin can do 2 things. The first is model parameter calibration. As we all know, the precise parameters of a heating supply system is very difficult to obtain. And we can simulate the room temperature with the DG. Then we compare the simulated room temperature with the measured temperature and try to minimize the difference between the 2 temperature curves by tuning the parameters of the digital twin. Then we can get a relatively good system model, and we can use that model to predict the room temperature change subject to environment temperature change and heat pump usage. The second thing that the digital twin can do is to do data-driven optimization. How to do that? First, we determine the control period. Then we use the tuned digital twin to look ahead several periods and predict the variation of room temperature subject to environment temperature change and heat pump usage. Then we find the control pattern of heat pumps at different control times in the look-ahead time span. Then we select the optimal control pattern and conduct the nearest control. Then the time window moves ahead by 1 period and repeat the procedure. Okay, now I give you another application of the digital twin of IES, which is the planning and the design platform for IES. I just give a very brief introduction. After my talk, Dr. Yan Kan-song, who is from my team, will give a more detailed introduction about this platform. Our platform is suitable for different scales of IES, no matter it is city, city scale, a scale of a city or the scale of a park. And in this platform, we can consider electricity, heat or cold, and gas. The renewable energy resources, energy storage systems are also considered in the platform. The platform has many functions. For example, load forecast. This load is not only electric load, but also some heat load, cold load, and the platform can do simulations. It can do equipment selection, market operation, economic evaluation, and environmental assessment. Of course, it can do optimization to the planning scheme. Those functions are grouped into 4 categories. The first one is data management. The second one is the probabilistic production simulation. Then the skill evaluation. And the fourth one is optimization. This is the general uh, procedure to use the platform to do the planning and the design of IES. First, the data management function block collects necessary information such as meteorology, and load data and distribute those information to other function blocks. Then a preliminary scheme is simulated. Uh, we need to do the probabilistic production simulation to see how this preliminary scheme is working. Then we do the evaluation. And if the performance of the preliminary scheme is not satisfying, it will be passed to the optimization function block. After optimize, the improved scheme will be sent back to do the simulation again. After several iterations of planning and design scheme will be obtained. In the platform, we developed several key techniques. For example, the regional heating supply system simulation, the thermal load forecast model, the heat cold power integrated system code simulation, and code optimization for IES. Some people just ask me why you need a digital twin to do the planning. What's the advantage of DT-based planning over traditional planning? I would say a DT is used for the IES at the planning and the design stage so that different scenarios can be compared and we can choose the best one from a couple preliminary things. The second advantage is that the DT can be used to support operations in the future. It's not only used in the planning stage, it can be passed to the operator and to do some technical support for the optimization uh, optimization of operation. The third advantage is that the DT can be used to do post-evaluation of the planning scheme so that we can find what's wrong if the system doesn't work as it is planned, and we can find clues to improve the IES. Okay, here comes the conclusion. I would say the digital twin has many advantages, and it will have very bright prospects. Our cloud CSS is open, and you are welcome to use the platform and feedback your ideas. And we are looking forward to any cooperation. Okay, thank you. I would like to answer your question.
Thank you very much, Professor Shenzhen. Now, if you conclude, share your video.
Yes, I'm trying to.
And the presenter, okay. And now we want to thank you very much for your very interesting talk about this very hot topic, that is the energy management in several ways, way of interaction. And now we have the three startups, the three companies that are involved also in these arguments. I'd like to become with the grown Acadis, and if the people from the company ask to me to become a presenter, I can reach. Okay, this is.
Yeah, give me the opportunity. Okay.
Silvio, I share to you. Okay, you can show your company, about your interest, and
Do you see
you have fun to conclude the talk. Your shared.
Do you see my hello? Do you see
like,
my video?
No, it's
Okay.
No.
Okay. Can we try to install the application? It's the problem that we have found today.
so
Okay.
the problem of energy management is very important. I'm working in the field of power devices, and so I have seen after we will talk about this with also Professor Shen, the opportunity to have right models for power devices, not only from an electronic point of view, but also the electrothermal point of view, because I know that is a very important issue. Anyway, we have still a problem with the sharing of the video from grown Acadis. We see gray.
I'm coming. Do you see me?
There is a very noisy echo.
I see a lot of.
We have a problem of echo, very, very important.
Okay. You see?
You are connected to devices. Are you connected with two devices? Because we have a big echo from you.
Okay. Do you see now? Sorry. Do you see now?
There are some gray box on your screen. I don't know what.
Okay. Give me the possibility to share the video. Paolo.
If you have two devices connected, you have to mute and eliminate the audio from one. Otherwise, we have a big echo in our audio.
Just one audio. One audio. I don't know why. Just a moment. I think head shoulder.
Anyway, let's try to go ahead presentation, but it's not very clear to see. Okay, there are so many problems from you, so I want to switch to Naples prototype. I hope that in time we can solve the problems from growing Acadis. So please, the people from PMP can share their presentation.
Good morning.
Good morning.
It's all clear, the image?
Yep.
Okay, so we can start. We are Power Maple Prototypes Laboratory, a company which was born in 2013, the spin-off of the Department of Electrical Engineering and Information Technologies of the University of Naples Federico II. The aim of the company was to study and develop innovative technologies and make power electronics devices that could exploit them. PMP Lab as a flexible and project-oriented organization capable to manage small lump sum EPC industrial projects and research projects, as well as to design and deliver special devices for industry.
Perché mi ha buttato fuori.
Company has established a long-term collaboration relationship with major groups operating mainly in power, oil and gas, industrial and automotive sectors. So the company main expertise areas are design of power plants and oil and gas plants, measuring systems and data sensing, and the design and construction of electrical converters. PMP Lab has gained huge experience in the years through many collaborations with major Italian and international industrial companies, such as NLSPA, for example, for the design, development, and maintenance of proprietary software for acquisition of thermodynamic variable measurements of generation groups. Also for international projects such as for ABB South Africa, for Johannesburg CI-LAM coal-fired combined cycle power plant, with proposal and feed for DCs, system, HV and MV electrical systems. Also for Turbomac SA, in Caterpillar Group in Switzerland, for engineering services, mainly electrical, control and automation and instrumentation. For EPC, cogeneration heating plant and combined cycle power plant projects carried out by the company Turbomac SA in Europe, Russia, Africa, and also Middle East. For CSPA Milan, the study and development of automatic voltage regulators, so AVR, and remote release logic, and also the design of the control and regulation systems of the test laboratories for high, medium, and low voltage equipment. Again, with NLSPA, this time for international projects, such as the design, supplier follow-up and commissioning of the regulation systems and control of the conventional part of the Mokotce nuclear power plant in Slovakia, and INC, process engineering and simulation services among various project teams of various plants, including combined cycle power plants and coal power plants in Italy and also South America. In the field of research, of research and development activities, PMP Lab has operated in the design and development of power conditioning systems with proprietary equalization technologies, with the main function of the system that are the compensation, the peak shaving of active power factor correction of network load with continuous adjustment of the power factor, and recharge of the storage system at the end of the discharge. Also, in the past 2.5 years, the partnership with the University of Campania and University of Nottingham within the European Union founded Clean Sky Research Program, the so-called Aspire project, for the construction of an inverter aimed to equip the aircraft designed with new generation MOSFETs and for other components. In conclusion, potential research and development, innovation and prototyping activities of PowerNAPLE Prototypes Laboratory are related mainly to applications and studies of new generation IGBTs and MOSFETs for static energy conversion systems, power conditioning and energy storage systems based on supercapacitors, and dynamic simulation and steady state analysis of high and very high voltage grids. Thank you for your attention, and you're welcome.
Okay, thank you very much to the people from PMP. I'd like to hear about the center to the people from Cloud EPS. If I write the person who will talk about this is Professor Yang Song. It's true or not?
Okay, may I share my slides?
Yeah. Okay. So now you are presenter. You can share your screen and you can present your very new startup.
Okay, can you see the slides?
Yeah.
Can you see my screen? Yeah, okay. Okay, good afternoon, ladies and gentlemen. My name is Yang Song from Professor Shen's research team. And I will follow Dr. Shen's report, and I'm glad to further introduce one of the platforms we developed, the Cloud IEPS platform. The IEPS, which is short for Integrated Energy Planning Studio. So firstly, I will briefly introduce the modeling and the simulation technique on the Cloud IEPS platform, and then I will show the features and applications of the Cloud IEPS platform on our website. So first, the integrated energy system incorporates many kinds of energy resources, networks, and loads, such as power system, heat system, and gas system. There is a complex coupling relationship among various energy systems. So in order to analyze such complex system, we propose a general modeling and a simulation framework. And also the digital twin of the IES is also built based on this framework. We also developed a simulation engine to support the further simulation-based applications such as reliability evaluation, planning and design, and operation optimization, and fault diagnosis. A typical IES incorporates two paths, the energy hub and the transmission network. And the energy hub model can be defined as a composite device where the energy produce, convert, storage, and consume. And the transmission model is the network where energy flows and transmit. In general modeling framework, we use these two concepts to help build a large-scale, complicated IES system. For the energy hub model, we use the LCP model to represent the energy conversion process between different energy forms. In this model, L and P represents the output and the input energy flow, and C represents the conversion efficiency. Here we give 4 examples, such as the heat exchanger, heat pump, steam turbine, and ice storage. They all have their unique LCP equations. Notice that because the Cloud IEPS platform is mainly developed for planning and operation studies. So we only use the steady state energy flow equation to model the IES. For the transmission networks, such as the heat network and the power grid, the transmission device model and the nodal-based network model are introduced. We use nodal analysis framework to gather the network equations. For power system, we have the nodal-based power flow equations, and for the heat system, we can form the nodal-based mass equation, energy balance equation, and looped pressure equation. And gathering all the equations, we will form a large-scale nonlinear algebraic energy flow equations. So in order to solve the nonlinear problem, we apply a decomposition and a coordination solution algorithm. So first, the entire system is decomposed into different subsystems, such as a power system, heat system, steam system, and the boundary devices. And then given a specific boundary variables, each subsystem can be simulated and calculated separately with appropriate solver. And then the results are sent back to boundary components, and a coordination solver is designed to solve new boundary variables. By iterating several times, the solution may converge, and we will get the final energy flow. So here is a simple version of the decomposition and the coordination solver for the heat system and the power system. The two subsystems are solved alternately in each iteration. So finally, by solving the energy flow for different time instants, we will get the energy flow for each snapshot, and we can estimate or evaluate the cost, the environmental performance, and reliability of the IES. So based on the modeling and simulation engine, we developed a simulation-based IES planning platform called Cloud IEPS. And the biggest difference between our platform and other softwares, such as the Homer, GridLabD, and the CI-LAM, and the biggest difference, the Cloud IEPS is based on energy flow calculation, but other softwares only based on purely energy balance equation. So our optimization results can consider the influence of the transmission network, but the traditional planning software do not support this feature. And then I will use our website to briefly introduce our platform. So can you see my screen? It's a blue page.
Yes, I can see it.
Okay. Then I will do it from the beginning. Okay. Sorry. Okay. So first, we can log into our website. It is called IEPS, and then we click log in. And there are many projects here. It's a project list. We will show one of our demo projects here. We open this project and we can see 4 function modules. The first is the data management module, and second is the topology editor, and third is the optimization, and the last is the evaluation. So first we can click into the data management module, and then we can enter in the latitude and altitude of the project location, and we will locate on the map, and then we can import the meteorological data from NASA, and then we will get the meteorological data such as the surface temperature and the solar radiation and the wind speed, which will affect the IES system. And the second library is the energy information, which we can import the energy price data, such as the fuel data, the gas data, and the gas price, the fuel price, and the electricity price, heat price, and the cold price. And the third library is the device. We can input the device data. In the device data, we incorporated many devices such as the electricity generator and heat generator, cold generator, storage, and transmission lines, transformers, and capacitors. And for heat system, we have the pipe pump and the heat exchanger. And the last is the load data. And we can import load curves and load models here. So after we load all the data, and all this data will distribute to the other function blocks, and then we enter into the second block. The second block is the topology editor module. It is used to build and edit and display system topology, which is the model of the entire IES system. And we provide over 30 devices to build the IES system. So before we run this optimization, a preliminary scheme should be designed in this editor, and then we can then we can get back to the optimization module. So in this module, and we can set the optimal function to set as to maximize the profit, or to maximize the economic environmental performance. So after we click the start button, and the optimization core will generate thousands of scenarios and carry out thousands of energy flow calculations. The results will be calculated in the scheme optimization module based on detailed operation data. And finally, the Cloud IEPS will generate several schemes for users to choose. And finally, after we get the optimization results, we can enter into the scheme evaluation module. And in this module, we can choose several different schemes and see the detailed evaluation results, such as the investment and financial data, environmental and financial data, and environmental performance, and the energy efficiency index. And all this data can be analyzed and can be exported for further analysis. Okay, this is a brief introduction and operation presentation of Cloud IPS. Thank you. That's all.
Okay, thank you very much to Yang Song for this nice and long presentation. So we can try to switch another time with the people from Grun Arcadis. I send the privilege of presenter to them, and
Okay, do you hear me?
yeah.
Okay, now I try to share the video. Do you see?
It's black now.
Again? I don't know.
We have to wait some minutes. Maybe your connection is not so
good. Yeah.
So fast.
So fast, it's so good. Yeah. Right. Now, do you see? No?
Not yet.
Try another.
On my side is still black.
I think that the connection is not good. Is share with you.
Okay, now we see. No, gray. Now it's gray. Before we.
From my point of view, I share my video. From my point of view.
Yeah, but they made that okay. Okay, no.
Do you think this? No.
Let's try to go ahead with this way, okay? No.
they are another class or another file.
So it's not, I don't know, Paolo, Paolo Pressiani, do you are able to see the screen, or is a problem only?
No, I don't see them, at least sometimes, but I see some gray areas.
Yeah.
So I'm giving some advices to Silvio and
Perhaps you should minimize the window of the WebEx meeting.
Yeah, maybe you have to minimize the window, not to use the full screen view.
Okay. Now?
Okay. We come to speak in this way. We come to speak in this way. Okay.
Right, it's okay. It's okay. Thank you very much. Sorry about
that's because we make the test before. It's for the next opportunity for you. When we say to make a test, we want to have this not possible. Anyway, go ahead. Thank you very much.
Thank you very much, you, Professor. Good morning, everyone. This is Sottocorno Silvio. I'm a founder from startup Growing Acadis. With this presentation, I'll try to explain our idea about green energy. This presentation starts introducing the startup. It continues with the market solution available today, but I think that you know better than me. Then I'll show you our solution and the application, at the end, our products. This is the startup team. Arcadis is a startup company in the green economy sector. When you know, the startup team is made up of people who cover the role necessary to achieve our vision that we have defined as building electronic products that increase energy efficiency. The team is composed of partners in green and professional skills that support us with their skills. It's a start of a European patent that describes the way to use renewable energy in an instantaneous self-consumption way. This is the start of the market today in the world. You know better than me. Standalone, where the renewable charge mainline the batteries. This is a situation we use when the grid is not available. The problem the system is that needs manufacturing the battery. The second, with connect. In this case, the energy is from the renewable is mainly used to the user, and the excess energy is fed into the grid. In this case, it's convenient to use this situation when the price of the excess energy sold to the grid is higher than the price purchases of the grid. So to solve this for a system like in this of this of the grid connect situation is that when the grid is switch off, the system switch off. A common feature of both configuration is that they require a lot of space, physical space to install the renewable generator. Our solution is a little bit different. We believe that it's important to increase the use of renewables. We have designed a product that can use with any type of renewable generator in a simplified way. And it is in the instant self-consumption mode to define a new configuration that we have called a mixing system. This configuration is composed from renewable, our product, the user, and the grid. The product works in such a way that it takes all the energy from the renewable sources to the load, and if the load needs more energy, it is taken from the grid. Of course, energy from the grid decreasing as the energy production from the renewable sources increasing. The advantage of this system is that principally reduce the size of the space occupied by the renewable, because the size is according to the real needs of the user. Lack of maintenance, and there is a dependency of the presence of the main of the grid. We find this system in a typical application, like in the home system or industrial system, but it's very interesting to use it in applications like smart city. We can find a solution by the e-bike system charging, or integrate our system inside other in outdoor user system in products that are already in our cities, like traffic management system. In this case, we have a partnership with Torino City Lab to test our idea in this particular thing. We do need some products. You have development 2 products. One of these is Energy Optimizer. Energy Optimizer is a product from the smart cities. It's a 500 watt power, and the main feature is use this product inside other devices. The second is under development, is the mixer. It's a product from the home, from the house. It's a 3 kilowatt power, and the main feature is that the user can be scalable. The input power of burst power of 1.5 kilowatt, according to the user needs and according to our technology. I want to leave finish my presentation with a phrase from Caravaggio that say, when there is no energy, there is no color, there is no form, we want just word, there is no life. Thank you very much. I'm sorry about the disappointed before.
Okay, thank you very much, Silvio. That's a very nice presentation. I hope that the technical problem does not give so much trouble for the people, because there are very important things from you, from PMP, from Cloud EPS. I see in these 3 companies, and obviously on the speech. Please, can you stop the sharing of your video, Silvio, please? And okay. And also from the speech of Professor Shen, a lot of topics of talking that we can use now for the next, let's say, 20 minutes of discussion. I'd like to give the talk to Mr. Shen, but the first question that I want to give to these people is, okay, my field of interest is on the simulation and also the characterization of power devices, no, MOSFET, IGBTs, new carbon silicon devices, CC devices. And the most important issue that we are giving in our research is about the electrothermal problems that can this device have. And the question is how much this deep problem, let's say very base problem, can be included in your simulations or in the solution of your elements, your devices.
Okay. Actually, Professor, can you hear me? There's a lot of noise. Professor?
Yes, I hear you, yeah.
Actually,
you can also switch on your camera if you want.
Okay.
So I don't know if my question is clear. How much the electrothermal problems in power devices can give problems in your very complicated simulations or devices?
Actually, there's a lot. The first one is for I did for those silicon devices, so for those converters, their dynamics, the time span of the time scale of those converters are very small. That means really we need to use very small steps to do the calculation. That means the computational efficiency is very low. For example, to simulate 1 second physical time, you may need 1,000 times of simulation time. That is not tolerable. That is not allowed for engineering use. So we have to speed up the simulation. So we adopt another computing technology. For example, the parallel computing, the high performance computing devices. And in the software, we adopt many algorithms, new algorithms. For example, some the shift frequency analysis method, some new technologies to speed up the simulation. Yes, there's a lot of difficulty.
Yes, I perfectly agree with your consideration. What about other people from the companies about the problems or the ideas that you have heard this morning? Eh? No consideration.
From PMP Lab. So, okay. We can say that we in the past developed a high reliability inverter for I don't know standalone uses in unborn areas. For instance, in Madagascar, where there was a problem about the maintenance, so that we designed and implemented three-phase AC/DC custom converters with high reliability, so that there is a double stage with in intermediate DC link bidirectional, so that it is able to work on the four quadrants of the diagram and PWM. So maybe this could be related to the electrothermal problem.
Yes, yes. We developed such a kind of tool. Actually, try to study the dynamics of those complex electrical devices. And so far, we just built the models, the electrical magnetic models or converters. If we want to do some maintenance, multi-physics models should be built. For example, the heat transmission model of those devices should also be built in the digital twin. So far, we can only simulate the electrical dynamics of those converters. So we can study their performance, their behavior in the circuit.
So is the same very old question, very old idea that the simulation of the device is concerning the ability of the circuit, and the electrothermal simulation of the PCB is concerning about the energy efficiency. No.
So far, we didn't build the model of the heat part, so we cannot start the efficiency of the device.
And another question that I want to give to all of you. More or less, all of you are involved in energy conversion, no? In one thing or the other one, the cloud EPS and also grown Arcadis. How is important the volume consumption of these devices in your project? How is important, how is compact your circuit when you go to design a new converter, a new circuit?
For us, it's important. It's the main question, because the efficiency of our electronic component in feature the on stage on start all the system, because we make a product in a self-conduction mode. The first analysis what we do is analyze the performance, the consumption profile, and then they identify the right dimension of the available sources. But all the system starts when the efficiency of our equipment is less or about the energy that we produce the renewable source. For us, it's very, very different. In this case, we have switched to the power of our product. We start with a small power, a two-step in this case. I explain? No, because a big converter needs have a good efficiency at the top, and not during the start and in the middle. That's okay.
Yes, understood.
It's difficult with all. For us, it's very, very difficult. And then you try to new way to switch on and to switch off the electronic component. find the right situation, and so on. This is it's our.
Okay, I have a question for Yang and Song about the software that they have developed. How is it's not a question, it's a curiosity, no? Because I imagine that if you want to simulate the grid connection very, very huge, you have also the possibility to use a very big computing. So how is the dimension of clouding computing that you are using now for your simulations?
Okay, let me answer this question. So yeah, for large-scale energy system model, the final equations we get will contains many dimensions, such as maybe thousands of millions of the equations. So we use the cloud computing devices to accelerate this process, such as the Professor Shen has mentioned for the cloud PSS. So the basic cloud computing framework is for the cloud PSS platform and for the cloud IEPS platform is similar. So for cloud IEPS, we haven't tested the largest system, maybe the system scale, the largest system scale we have that the system that this platform can make. But generally speaking, the simulation scale is not limited by the algorithm, but only limited by the computing resources. So if we have enough computing resources in the cloud, we can simulate the very large scale power system or energy system. So in Professor Shin has mentioned that we have made a large scale power electronic system that is a secret benchmark, and that system has more than 80,000 switches, and the node numbers more than 100,000 buses in that system. So when we're using the computing resources in the cloud, we don't have the computing. We don't have the limitations for that on the scale of the simulation case.
Okay.
That's my answer.
Yeah. It's a good answer, and I have understood perfectly. And I don't know if Professor Shenzhen would like to make a question to other participants.
Well, I have a question. Do you hear me?
Who are you?
Yeah.
Oh, okay. So I have a question. I saw that you mentioned digital twin of a power grid or power generation system. So where is the physical part? You are talking about digital twin. Where is the physical twin? So for me, it's only a simulation rather than a digital twin. Am I right?
Yes, you're right. Actually, the digital twin needs a physical part. And so far, the application, I give two applications. One is about the planning and the
Yeah.
design. The other is the control. Is the control of the heating supply system. The heating supply system has many sensors. It will send the room temperature, measure the room temperature, environmental temperature, and some other conditions. Then sent to our platform. And we use those information to tune our physical twin. And we find the control for the physical part. So then the physical part and the cyber part construct the digital twin.
So you're talking about this is the digital twin of a part of the system, not the entire system.
Don't wait. Sorry. I would like to give this advice for all. Okay. Before to make your question, please introduce yourself, because not all.
All right. I'm from Smart Factory Institute. So I used to be a student at Tsinghua University Electrical Engineering Department. So I used to work for Siemens for 19 years. So I know that Siemens has a similar product called PSSE. So very similar to this, intelligent energy planning software, but it's only the simulator of the power system rather than the heating part. So yeah, I see that when you talk about this digital twin, it's only a part of that a part of the digital twin of your entire power system, right?
Okay.
So,
Okay, my understanding is digital twin, according to its definition, it's also a kind of simulation. And it has its physical part. And the digital part and the physical part need to synchronize. And then in the physical part, we get information from the physical part. Then we can reduce its future state using its cyber counterpart. Then feedback the optimal control to the real world. So then we get to the closed loop. We get the loop closed. So that's my understanding about this point.
Okay. Do we have other question from the audience? Okay, if we don't have any question, and if all the people from Professor Shergen, from people from Grona Cadiz, from people from Power Naples prototypes and Cloud IEPS is enough, I'd like to close this meeting, and I want to sorry. I want to give my thanks for all the people that connected this morning. We arrived to reach more than 40 people for the first webinar, not the webinar that was made by Gelson, that was in another contest, but this opened webinar, I think that is a good success. I hope that the people involved in this morning have now much more links in order to improve their research, their job, and also the opportunity to have new ideas, but also, if it's possible, new partners. If you are able to link your ideas of business on this topic together, it will be a success for the CI-LAM project, because one of the aim of CI-LAM project is exactly this, to grow up cooperation in such topics. So thank you very much to all, and see you next webinar that will be held in 26th of June. and the topic of this new seminar is about toward zero breakdown from research to predictive maintenance. The keynote speaker will be Professor Sergio Camalieri from University of Bergamo. Okay, thank you very much. See you.
Thank you.
Bye bye.
Thank you.
Bye.
Thank you. Bye bye. Good.
Thank you. Bye.
Bye bye.
Bye.
Bye bye.